Hello everyone, and welcome back to another video where we are going to be solving the driven harmonic oscillator right here. You could think of this as the equivalent of, we have some spring here, like a mass on a spring right here, and somebody decides to come along and basically just like, I don't know, give it like a tug or something, give it a tug downwards, or just apply some external force to said spring. So yeah, let's get into solving it. This will be fun. So by Newton's law, we know that F is just ma, meaning we have ma is equal to r minus k times x plus our function of t, like our extra driving force. I'm going to divide both sides by m just to get the acceleration by itself, which I'm going to write as an x with two dots on top to represent the derivatives. And then we have a plus f of t over m. And to solve this, we're actually going to make use of some Laplace transforms. But before we do that, just to simplify things quite a bit, I'm going to define the variable omega. See if I can actually write. Omega is equal to, omega squared is equal to k over m. This is just going to help with a lot of the calculations later down the line with residues, etc. So, taking the Laplace transform of both sides, we end up getting, on the left-hand side, s squared times the Laplace transform of x minus our initial position times s minus our initial velocity, which is equal to the Laplace transform of the right side, which is just going to be minus omega squared times the Laplace transform of x plus the Laplace transform of f of t, which I'm just going to call capital F of s, divided by m. And in order to apply the inverse Laplace transform, or the Laplace inversion theorem, or Mellon's inverse formula, what we're going to do is just get the Laplace transform of x on its own. So to do that, I'm just going to add this to both sides to get L of x times s squared plus omega squared is equal to our initial position times s plus our initial velocity plus our f of s over our mass. And then I'm just going to divide both sides by this, meaning that our Laplace transform of our position is going to be equal to x naught s plus v naught divided by s squared plus omega squared plus f of s over m times s squared plus omega squared. Now the reason I've split it up like this instead of making it one continuous fraction is really just because when we apply the inverse Laplace transform, we're going to be taking this as a chunk really, or that's really going to be two chunks, and we're also going to take this on its own because we're going to do some kind of special stuff with that. So really just jumping into it, I'll write this on the side. We know that if we have the Laplace transform of, say, x, and we want to apply the inverse Laplace transform to it, this is just going to be 1 over 2 pi I times the integral over some contour, I'll explain what contour is in a second, of e to the st times basically our Laplace transform, ts. But our contour is basically chosen so that it encloses all of our residues. So say, for example, our residues are like at, well, I and like negative I or something. Basically what it is a semicircular contour like this, where we're going this way, this, and it basically just ends up being the integral, at least, the sum of the residues of this function right here. But then you have this 2 pi I here, so really the inverse Laplace transform is just the sum of the residues of that function, which is really cool. I'll have to find a proof on that sometime later. That'd be a fun video. But anyway, to the math. So to do this, we're just going to take this in 3 chunks, really. So first, we're going to find the inverse Laplace transform of x naught s over s squared plus omega squared. So we need to find the inverse Laplace transform of this. So to do so, we are going to, again, just apply the integral. So 1 over 2 pi I times our integral over just gamma x naught s e to the st divided by s squared plus omega squared ds. Now, we can just apply complex analysis here. This isn't too terrible. So again, it is just the sum of the residues of this function right here. And you'll notice that our poles, if we set this equal to the denominator equal to 0, because the numerator is never going to be 0, or won't cancel out any of our poles, I should say, really. If we solve this, we're going to get s is equal to basically plus or minus omega I. So, again, just applying this, or really I should have factored this, so it should be s plus omega I, s minus omega I. These two are equivalent, and basically here are the location of our poles. So, just applying this, what we're going to get is let me zoom out a tiny bit. What we're going to get, I'm going to start by plugging in this right here, actually. So we're going to get our s minus omega I times x naught times omega I e to the omega I t divided by s, well it's s squared plus omega squared, but I'm just going to factor it. So s plus omega I, which is just going to be 2 omega I. So 2 omega I times, well, technically 0, but I'm going to write it like this. So this way, these cancel right here, and we are left with an actual residue and not just a 404 error. And so yes, this is going to be our first residue right here. So to get the second one, we're just going to take the same thing, but basically just, well, flip the sign of what we're plugging in. So we're going to have a plus in x naught, or I'll start with, I'll make it symmetrical, I suppose. So an s plus r omega I, and then an x naught times r minus omega I e to the minus omega I t divided by minus 2 omega I times our s plus omega I. And again, these cancel. I'm not being too rigorous with the limits, and I apologize. This is just for brevity. So just to write this out as one just like large term, what we're going to get is x naught omega I e to the omega I t divided by 2wi. And you'll notice here that these minus signs actually do cancel, so we're left with plus x naught omega I e to the minus omega I t divided by 2 omega I. And you'll notice we have a common denominator, and also that the omega i's do cancel. So what we're left with here actually is just, I'm going to factor out the x naught times e to the omega I t plus e to the minus omega I t divided by 2. But this right here is really just the definition of cosine, sort of, cosine of omega t. So this bit right here is just cosine, or x naught cosine, pardon me, x naught cosine of omega t. So yeah, that's our first bit of our inverse Laplace transform. Let's go do the other bit, which should be a bit simpler actually. So going off to the side here, what we're going to have is our inverse Laplace transform of our v naught over our s squared plus e, or no, not e, pardon me, omega squared. I was thinking of the integral, which is going to be equal to 1 over 2 pi I times our integral over gamma of v naught times, well, if we v naught over s squared plus omega squared times e to the st ds. So again, just finding the residues of this thing right here. Our poles are just going to be the same, so I'm just going to plug and chug, for lack of a better phrase. What we're going to have here is just s minus omega I over s plus omega I, s minus omega I, and this right here is just going to be 2 omega I when in the limit, times RV naught times e to the omega it. Doing our second residue, what we're going to get is an s plus omega I this time in the limit, times v naught times e to the omega it, divided by minus 2 omega I, and then an s plus omega I. And again, these are just going to cancel. These are going to cancel, meaning we are left with a v naught e to the wit over 2 omega I, minus this time v naught e to the, I'm sorry, there should be a minus there, minus omega it divided by 2 omega I. Now, what you'll notice here is that we again have our common denominator, but we also have a v naught, a common v naught. So I'm just going to factor out a v naught over omega, and let's see what we're left with. So we have a v naught over omega, leaving us in the parentheses with e to the omega it minus e to the minus omega it divided by 2I. But you'll notice here that this is just the definition of, or well, not the whole thing, just this right here. This is just the definition of sine of omega t. Those things are completely equivalent, meaning that the second half of our, well, second third of our Laplace transform is just going to be v naught omega times the sine of omega t. So, with that out of the way, we can now conquer and evaluate our third bit of our Laplace transform, inverse Laplace transform, which is this right here. So, scroll over even more. We need to find the inverse Laplace transform of, let's see, 1 over m. I'm actually just going to put the 1 over m out of the parentheses just for brevity. So we have an s squared plus omega squared times f of s right here. And I'm actually not going to be using this complex analysis approach for this one, mainly because you can't really, with this term right here, f of s is just completely arbitrary. So what I'm going to do actually is just take advantage of the convolution theorem for Laplace transforms, which basically states that if we have two Laplace transforms, so like say f and g, those are both Laplace transforms of the normal functions f and g in lowercase. So if we take the inverse Laplace transform of this is just going to be some integral of f of, say, t prime times g, t minus t prime dt, t prime dt prime. This is all that states. So basically, just taking advantage of this, what we're going to have is, let's see, well, we know the inverse Laplace transform of f of s. We basically just defined this earlier to be, just normal f of t. But what we actually did when we were evaluating the sine bit is find the inverse Laplace transform of 1 over s squared plus omega squared, which we found to be just this sine term right here, sine of omega t, and then also that little bit tacked on as well. So really what we have here, using the convolution theorem, is 1 over m times the integral from 0 to t of the inverse Laplace transform of our f of t, which is going to be f of, say, t prime, times the inverse Laplace transform of our 1 over s squared plus omega squared bit, which is going to be sine of omega, but then we're going to have t minus t prime dt prime, and I'm just going to put the omega outside here. So yes, this is our third and final bit of our inverse Laplace transform. So all we really need to do now is tack everything together, and we've solved it. So I'm just going to make some space down here. So our x of t is just going to be equal to x naught times our cos of omega t plus our initial velocity divided by omega sine of omega t, and then we're going to have plus, I'm going to have to zoom out for this part, plus 1 over omega m times the integral from 0 to t of f of t, or f of t prime, pardon me. Whoa, that's a big parenthesis. Let's calm down here. F of t prime times the sine of omega. I'm going to zoom in just to write this part. Omega t minus t prime dt prime. So yes, this is our solution to the driven harmonic oscillator. And to just kind of like, I don't know, fact check this, you can always plug in f of t equals 0, and you'll get this whole thing. You'll get this whole thing right here equaling 0, leaving you just the normal harmonic oscillator solution. So yeah, I hope you all enjoyed. And although I do feel like I explained it before I say goodbye, the reason I wasn't too formal with the complex analysis is really just because you can always just look at a table for Laplace transforms. Like, you don't always have to do complex analysis. I thought it'd be fun to, you know, kind of go half a step towards being more rigorous. But anyway, at any rate, I hope all y'all enjoyed, and I'll see y'all in the next one. Goodbye.